Hello, today we are going to learn about Green's theorem and Green's function. So let's say we have some arbitrary function phi, which is function of a space vector r, and we have some other arbitrary function psi, which is the function of two three-dimensional vectors r and r prime. Both of these are scalar functions. So given these two arbitrary functions, Green's theorem tells us that the integral of phi Laplacian of psi minus psi Laplacian phi, this is volume integral, is equal to the surface integral phi gradient of psi minus psi gradient of phi. This is our surface integral. Alright, so what are these volume and surfaces? These are, say, any closed volume V, and the surface enclosing this volume is S. This is, we can say, a closed surface, so we can indicate this by the closed integral symbol. So this is called Green's theorem. So how is Green's theorem going to help us in solving our boundary value problems? So we have a volume V enclosed by a surface S. We want to find phi of r, which is here this phi is the electric potential, where r is some point in the volume V. Alright. So if we want to make things clear, we should have a coordinate system because we are working with vector quantities x, y, z. This is some point r which is inside this volume, and this is the vector r indicating it. Right? So the problem was to find the potential given rho of r in volume V and the Dirichlet condition, in which the potential on the surface is given, or the Neumann condition, which means that the gradient of the potential on the surface is given. This is discussed in the previous video on Poisson's equation. Alright, so how is this going to help us solve our problem? So what we are going to do is, in this equation, where phi and psi are arbitrary scalar functions, we are going to substitute phi with our electric potential. So the notation remains the same, that is a good thing. Maybe we will use some other variable, r dash, to indicate this electric potential. and for psi we will substitute this with something called a Green's function, which is called Green's function. Now what is special about this Green function? This is not any arbitrary function like psi. Green's function has the property that the Laplacian is equal to minus 4 phi delta r minus r prime. Here the dashed or the primed del operator means that we are taking the derivatives with respect to this variable. Alright. So this is the well-known Dirac delta function. And the Dirac delta function has a very important property, that is the integral of the Dirac delta function times any arbitrary function in a closed volume V is equal to phi of r if r is in V and 0 otherwise. Alright. So the Dirac delta function has this property which we will use later. This, the del square of psi, if we come here, because our psi is now g, so we can write this as phi of r dash del dash square g. If you notice, we are changing the variable of integration and the variable from the unprimed variables to the primed variables. So it's just a change of variables. So that is just whatever your convention is. We'll do the integration here, and this is simply the same thing. So now we know that this thing is nothing but delta r minus r dash, because that is how we have defined our Green's function. This is by definition, and by Poisson's equation we know that this Laplacian is nothing but, this remains the same, the right hand side does not change. Now we can just separate this integral. So here if you see, by the property of the delta function, this is simply this. Now when is this true? When r is inside the volume V, and this is a good thing because in our problem we are trying to find the potential inside the volume V. Simplifying all of this and separating out what we need to find, that is the potential at r, we finally arrive at the equation that we are interested in. So in case of the Dirichlet boundary condition, you will notice that this will be given to us, alright? And here there are basically two parts in this integral. One involves the gradient of the potential and another involves the value of the potential, and all this is required on the surface S. In the Dirichlet condition, of course, we only know the value of the potential or the potential on the surface and not the gradient. So we have to select G such that this is 0. This part becomes 0. So basically G of R dash is equal to 0 on S. Alright. Specifically for R dash on the surface. So on the surface, this function should be 0. And if this function is 0 on the surface, then our potential simply becomes, remember that the Green's function may not be 0 at all points inside the volume, it only needs to be 0 on the surface. This function is known to us because we know phi of r on S, phi of r prime on S. So these are the two conditions that the Green's function needs to satisfy. How do we find such a function is something which we will tackle in the next video. Now let us look at the Neumann boundary value problem. Here we know the gradient of potential on the surface. So going back to our condition for our equation for the potential, here we know the gradient of the potential. So we would like to eliminate this term, and to do so, the most obvious thing that you would want to do is turn this to 0. Alright, so we say that we select the Green's function such that the gradient of G times the surface element is 0 for all points on the surface. Is not possible. Why is it so? So this is divergence theorem. Using this, we can basically find that the surface integral is equal to the volume integral of the divergence of this, and we know that the divergence of a gradient is simply the Laplacian. I'm sorry, here we'll have the volume, and this we already know as minus 4 pi delta r minus r prime, and by the property of delta function, this is simply, I guess, minus 4 pi, because remember that we are solving the problem for r in V. So the integrand, which is the gradient of G dotted with the area element, cannot be 0 for all points on S, because if this is 0 for all points on S, then this integral will never give us a non-zero value. So the best that we can do is select this to be a constant, which turns out to be minus 4 pi by s, where s is the total surface area of the surface S. Here we summarize all the results that we obtained in this video.